In this video, we are going to take a look at applications for the second derivative of a given function. What we're going to need to do first is define one key term, which is concavity. So given the function f of x that I just drew, this part of the graph that looks like a U shape is what we would classify as concave up. And this part I'm highlighting in red, which is an upside down U shape, is what we would classify as concave down. And so concavity really just speaks to the shape of a function's graph. But more appropriately, and what we're going to be looking at, is defining these in calculus terms. So we're going to say a function is concave up when, and we're also going to set up for a function is concave down when, and give descriptions of those in calculus terms. So the blue you're going to see go on this graph is all in regards to sine of the slope. And so notice for this red portion, the slopes start off very positive, gain less and less positive as you move up the hill until you get to a slope of 0 at the top, where this graph has a relative maximum. On the other side, the slopes start becoming negative, more and more negative as you go down the hill. Into the green section of the graph, the slopes are still negative until we get to the low point on the graph, where the slope is 0 and where the function has a relative minimum. And then the slopes become positive and become more and more positive as you move off to the far right of this graph. And we've got the separation point in the middle where the graph changes from red to green. So let's inspect the green part first, the concave up portion. And notice, since the slopes move from negative to positive, the slope values themselves must be increasing. But using a different word, that must mean that the derivative of the function is increasing, because derivative defines the slope values. So f prime of x in this case would be increasing. And if we go one more level down, this must imply that the second derivative for this given function, if f prime is increasing, that second derivative must be positive. And so in calculus terms, that is the true definition for a function being concave up. Now, if we look on the red portion of the graph, the concave down portion, notice its slopes are decreasing, moving from positive to negative, which must mean that if we think of that in terms of derivative, the derivative of the function over that span must be decreasing. F prime must be decreasing, which again, going one more level down, must mean that the second derivative of this function has negative values. And so those are our calculus definitions for concave up and concave down. But it leads into one more thing, which is known as the point of inflection, which is any point on a graph where the function changes concavity, either from concave up to concave down or concave down to concave up. Direction doesn't matter. So when I look at where the slopes change direction, this must mean where the derivative changes direction as well, the first derivative. And this must mean that f double prime, the second derivative, changes signs. And we can confirm that on our graph. When we change from concave down to concave up, the second derivative would be changing from negative to positive. And so what we'll finish up with is analyzing concavity and points of inflection using the second derivative of a given function. And we'll do that with the function f of x equals x cubed minus 4x squared plus 7x minus 2. And so step 1 to carrying out this analysis will be to evaluate the second derivative. Can't do any analysis with the second derivative unless we have it. So our first derivative, f prime, would be 3x squared minus 8x plus 7, just by using the power rule. And our second derivative would become 6x minus 8. Step 2. And in this step, what we're going to need to think about if we're going to determine concavity is we need the sign of the second derivative and where the sign can possibly change. So this must mean that we're going to find all x values where that second derivative equals 0 or does not exist, much like critical values for the first derivative. And so setting our second derivative equal to 0, the 6x minus 8 equal to 0, we'll get an x value of 4/3. And for the does not exist case, we don't have any of those because we are working with a polynomial. Step 3. Create a second derivative sign chart. An organizational tool just to help us figure out signs and help us analyze our concavity. So on the second derivative sign chart, the only value we care about is 4/3. And we're going to use test values to either side to determine the signs for all intervals on the second derivative. So a test value to the left of 4/3 would be 0, one to the right would be 2, and we'll plug those into the second derivative. Substituting in 0 would give us a negative value, so this entire interval, all the way up to 4/3, must be negative. There was no other spot for it to possibly change signs. And substituting in a 2, we get a positive value, which means everything from 4/3 off to the right must be positive values. In step 4, the only thing left to do is the analysis. So, we are going to say that our original f of x function, that cubic, is concave down when the second derivative is negative. And this is going to happen on the interval -infinity up to 4/3. We will also say our function is concave up where the second derivative is positive. And this happened on the interval 4/3 to +infinity. And the last thing we can analyze is, since the second derivative equaled 0 at 4/3, and the second derivative changes signs around this value, we can conclude that f of x has a point of inflection at x equals 4/3. Noting that the reason why we can call this point of inflection is the original function is also defined at 4/3. And that does it for our second derivative analysis, everything that we can read, which includes concavity and points of inflection. And all that's left to do is practice this with a lot of different types of functions. Thank you for watching.